welcome to Wednesday's edition of Cracking the Cryptic, where today we've got a puzzle that has jumped straight to the head of our queue in terms of Sudokus we're going to show you. It's called Quad Sums Sudoku. And it's by Udakos. Udakos is one of my favourite setters. And Mark, actually, I don't know what he was doing, but he's had a go at this puzzle, which I think has appeared on Logic Masters Germany. I may be wrong about that, by the way. I don't know where exactly he got it from. But he did it this morning and immediately rang me up and said, "You've got to do this puzzle in a video. It's just so brilliant." So that's exactly what I'm going to try and do today. It's intriguing. I've just been looking at the rules before I turned the webcam on. And I don't think I've seen this rule set before. And if that's right, it could be a completely new type of Sudoku, which is very exciting. Anyway, I will read you the rules in a moment. The first thing I need to do today is to announce some winners. So, well done, Andrew Young, because you have won the murder mystery. Your name came out of the hat. You successfully, obviously, solved the puzzle, and you were selected as the winner from about 700 people. So it is really your lucky day. And yeah, we'll be emailing you to find out which piece of merch you would like. Well done. And also for Heatwave, which is our Patreon reward for August, the Grockles created. The winner is Anos Sørensen. I hope I'm saying that correctly. Mark tells me that's a Danish name. So very well done to you two, and we'll be in touch about your merch as well. So fantastic. And I think, yeah, there was 600 or 700 correct entries for that, maybe more actually, for Grockles. Yeah, it's a good day for those two gentlemen. Now, what else do I want to mention? I've got a list here today. I hope you've had a look at the crossword video that we released earlier, 10 a.m. this morning. We released Mark's solve of this very, very clever US crossword from the Lollapuzzoola Championship by Brooke Husic. And yeah, it's a very entertaining video. Because Mark gets a bit stuck at the start, which is, you know, I've watched Mark solve cryptic crosswords for about 20 years, and seeing him get stuck is always a treat. Yeah, but also it's just a fantastic. The theme of it is just very, very clever and amusing. So, and you can have a go. So check that out if you haven't had a look at it. And in fact, on Patreon, we're going to be releasing a video of Mark solving the Times Monthly Special, which is something we try and do every month on Patreon. So that's coming out tomorrow. Other than that, tomorrow night is also the day when I will be resuming my quest to complete The Witness. I tried to schedule the stream. I tried to schedule the stream last night. So if you do follow the channel and you subscribe and you've clicked the bell icon, you should have got a notification about that. I don't know if that's worked or not, but I hope it has. And I'll also tweet when the stream goes live tomorrow evening. Our Twitter is @CrypticCracking. Right, with all that said and done, I don't think I had any other instructions I had to pass on. No, I can't think I did. So let's have a look at the rules to this one. They're really short today. We've got normal Sudoku rules apply. 3 of the 4 digits touching a circle sum to the 4th digit. Not all circles are necessarily given. So let us look at these squares here and just have a think about what this means. So let's say that this was a 7. Then I think these 3 squares would have to be 1, 2, and 4 in some order, because that's the only way. Oh no, hang on. No, that's absolute rubbish. Oh my goodness me. I've suddenly realised that I could do this. Oh, this gets complicated indeed. Right, well, this was a very good example to pick. If only to make myself look stupid in front of a lot of people. Right, so there, yeah. I mean, there seem to be a lot of ways of making these add up to 7. So we're going to have to think about this quite hard, I think. Not all circles are necessarily given. I think what that means is you can see there's no circle joining these 4 cells together. So let's imagine that was a 6 and that was a 1, 2 and a 3. Then I think that's fine. So you could see that in theory there could be a circle here because 6 is the sum of 1, 2 and 3. But there isn't a circle, and that doesn't mean that this can't be an arrangement of those digits. All we know is positive information, i.e. we know that the condition definitely applies to this 2 by 2. It definitely applies to this 2 by 2. etc. Do have a go. The way to play is to click the link under the video. Now I get to play. Let's get cracking. I was just thinking then, do I know anything about the difficulty of the puzzle? But actually I don't. I didn't ask Mark that. I simply took his instruction, and I'm going to have a go now. So where shall we start? I think we shall, presumably we've been given digits for a reason. So 6. Well, 6 can definitely be 1, 2, 3. Ah, okay, no, right. Well, it's true. 6 could be 1, 2, 3, but it could also be part of a sum. If I add 1 and 2 to 6, I would get 9. So I think I have to add 9 as a possibility to those. Now, I guess on this side of the 6 clue, I've got to be incredibly careful because, for example, now I've realised I could go double 1 here and then 4 here, and that would be correct because 1 plus 1 plus 4 does indeed equal 6. So I think goodness only knows how many options this stuff has. Oh, right, okay. Well, let's put the options into there. 1, 2, 3, and 9. And what I'm just thinking here is I've actually, these 6s in the grid are pinching a 6 into this one as well. That might be interesting because it's going to get very close to creating some... it's not quite going to work. Ah, right, I thought this was going to be good. Because now if we think about this white dot here, we know that there is a 6 somewhere in it, and the other digits are 1, 2, 3, or 9. So we've almost got something quite exciting, but we haven't quite, because we haven't got actually a quadruple there, because the 6 gets in the way of it. Same is true here, the 6 gets in the way of it. So I think the expression we're looking for is bobbins. And actually, we can put a 6 in one of those cells. Wow. Now I'm absolutely stuck. I quite like the rule set. It sort of appeals to me. Because if you've done a lot of killer Sudoku, you're very used to these sums of digits. But having said that... okay. Right, let's have a look at box 9. Yeah, this is quite good. Right, what would happen if there was a 6 in one of these two cells? Well, then we would have to think hard about this 2 by 2. Because the only options for those two digits would then be 1, 2, 3, and 9. And now we've created a problem in this box. So let's just hypothesize this is a 6. This box is now broken because these 6 digits can only be selected from 5 different numbers. So axiomatically, we are going to have to repeat one of those numbers in order to fill the boxes. And if we repeat one of the numbers, we've broken the rules of Sudoku. So that, yeah, okay, this is potentially a good thought, because that means I can remove 6 as an option from these. Obviously, these are now, we have no idea what this domino is anymore. But now we do know there's a 6 here. Oh. Actually, maybe that's a bit disappointing. No, it's not. It's not disappointing at all, because now actually I can place the 6 in box 3 by exactly the same logic I just did, which is if I put the 6 in here, this digit will have to be a 1, 2, 3, or 9 because it's on a white dot, and then I'll have 5 digits in the column that have to be selected from 4 different numbers, and that won't work either. So you can't put a 6 on this white dot. So just to go through that, if you put a 6 here, obviously now those squares have to be 1s, 2s, 3s, or 9s, and that means you've got 5 digits in the column that can only be 1s, 2s, 3s, and 9s, so that won't work. So I think we can take 6 out, we can place 6 here, which is sort of good, but it doesn't actually do anything, does it? It limits a 6 slightly in box 2, we've got the sign of the devil making its appearance in the puzzle. Damien Thorne. I did a video recently where I couldn't remember the surname of Damien from the Omen films, and I got inundated with people reminding me. Thank you. So 6 is at one of these squares. Maybe this dot now then. Because if we look at this column, I have got a quadruple now. So this domino here must be selected from the other digits. That's 4, 5, 7 and 8. Right, okay, well that's a little bit interesting. Because right, yeah. So, question 1. Is this a 4-5 pair? Answer, no way. Because whenever we're adding 3 digits together that have to be different digits, and they do have to be different on this white dot, we're going to get to at least 6 as the sum that we're aiming for in here. So if we did put 4 and 5 here, we would know they would be part of the arithmetic, the sum, so we'd have to be 4 plus 5 plus another number to get to a higher number, and that other number cannot be a 0. So it would be at least 4 plus 5 plus 1 equals 10, which is broken. Now that's interesting because that means there is definitely a 7 or an 8 in here. They can't be both, again, because 7 and 8 can't be part of the sum. If you try and make 7 plus double 1 in this box won't work. 7 plus 1 plus 0 is also bad. So there must be one of 7 and 8 and one of 4 and 5 in this box. And the one that's 7 and 8 is the sum. It's the total we're aiming for. So if this is a 7, that's a 1-2 pair. And if this is an 8, oh, okay, if it's an 8, this could be a 1-3 pair or a 1-2 pair. Okay, alright, but there's definitely a 1 in this domino, for certain. Because we know that the total we're aiming for is 7 and 8, so that gets rid of a 1 there. Do we therefore know there's a 1 here or not? What are the options for 6 again? 1, 2, 3. Yes, we do, because we know we're always using 1s and 2s in each of these 6 thingies, because it's either 6 plus 1 plus 2 equals 9, or it's 6 equals 1 plus 2 plus 3. So there is a 1 in that domino, which means there's a 1 in this which means there's a 1 in this domino, where there is also a 6 pencil marked. So that is a 1-6 pair. 1 is not in those cells. Which means that 2 is in these cells. So we've just proved there's definitely a 2 in all of these 6 related 2x2s. So there's now no 2 up here. Which means that square is a 2, I think. Just doing the logic there, that means that those are not 2. This is just beautiful. Now I've got a 1-3 pair here. That means 7 can't be involved in as being the sum, the total, because 7 is going to be 1 plus 2 plus 4. So I can remove 7 from those. Right, okay, and we can't use 5, because 5 plus 1 plus 3 is 9. So we can get rid of 5. And this was going quite well until I just stumbled there. So what does that all mean? So I've got this quadruple here, so I must remember that. So I've got a 5-7 pair to place in the rest of the column. Whoops, let's central pencil mark that. I've got, this is an 8-1-3-4 quad sum. This one still seems to have the option of being either 9 equals 1 plus 2 plus 6, or 6 equals 1 plus 2 plus 3. Ah, yeah, got it. Right, now I'm going to look at this one. Because that dot can't have a 1 on it, because the 1's over there in box 9. So what's given this is the sum of 3 different numbers, and it is different numbers because this dot does not cross a box. It must be 2 plus 3 plus 4 equals 9. So these squares include a 4. Ah, no, better than that. The 3 in this quadruple, and we know there's a 3 because we know it's 2 plus 3 plus 4 equals 9, is now shifted here into the same position as the 2. So this becomes a 4-9 pair. This is ridiculous. 4-9 pair. This becomes a 2-3 pair. That means those are not 3s. So this is a 9 equals 6 plus 1 plus 2. This is 4-9. Those squares at the bottom have got to be 5, 7 and 8, I think. Oh, I see, and that's the same digits up the right hand side of column 9. And this one is, well, this has got a 9 on this dot now. So we're summing to 9 and we're using a 1 and we're not using a 2, so that must be a 3-5 pair. That's not a 5. Oh, I see, and that's not a 5, so that's a 7, that's a 5, that's an 8, that's an 8, that's a 7, good grief, that's a 5. I love this. This is a 2, 7, 9 combination, and that's a 4, I think. Now these 2 7s and 9s up here are on white dots. Right. Yeah. Ah, no, these cross the boundary. Oh, you rotten thing. I was about to make loads of, or announce lots of nonsense, I think. Is that a sensible thing to do? The answer is no. Do not announce nonsenses. 7. Okay. Okay, right. One thing I can do here, I think, is I can conclude that if we take either this 2x2 or that 2x2, you can't have 9 and 7 in the same 2x2. That would be impossible because I can't make these 2 squares double 1. So 9 would be the highest number. That's going to be the sum. We're going to have to add 2 numbers to 7 to get to 9. Well, the only 2 numbers that would work arithmetically would be 1s, and you can't put 1s in the same column of a Sudoku. Now that is interesting because that means if I can't put 7 and 9 there and I can't put 7 and 9 there, the only way you can configure 7 and 9 in the column is those 2 squares. The 2 must play gooseberry and keep them apart. Now, what does that mean? So if this is 7, this is 2, these 2 squares are adding up to 5. But this is tricky because they could be 2 and 3, or they could be 1 and 4. And if this is 9, these are adding up to 7. And they could be all sorts of things, presumably. Yeah. It's very interesting. Every time one of these white dots crosses a sort of box boundary, it becomes horrendous. Okay, so I think we're going to have to look for something else now. Now, can I do something with this? Maybe not, I'm not sure. Box 5 I can see is constrained. Yeah, box 5 is very constrained, especially that cell. And this cell's constrained because it's part of 3 different sums. Let me might use colour to show you what I mean there. Let's colour those in like that and that in like that. So you can see that yellow is summing that 2 by 2, purple is summing that 2 by 2, and blue is summing that 2 by 2. So this little square here is part of 3 different sums. Now, I don't think that can be a high number then, because there are 3 different ways of making 9, but I can't for the life of me think about how I'm going to... Hang on. Yeah, okay. I can see how to rule... I don't know. I think there might be a few ways of ruling out 9, but one way of ruling out 9 is if we try and put 9 in the middle, we've got the 3 different ways of summing to 9. Use the digits 1, 2, 3, 4, 5 and 6. So that would mean that these 7 cells have to be filled with those 6 numbers, and that's impossible. Yeah, the other way of thinking about it is that you'd have to put a 7 and an 8 into this cell, because you can't put 7 in a sum adding to 9 without using double 1, and this cell definitely can't be 7 and 8 for 2 reasons. Firstly, it sees 7 and 8 in the row. Also, it can't be a Schrödinger cell and simultaneously be 2 things at the same time. So that is not 9. Now, 8, I think, is going to run into the same problem, isn't it? Because here, the ways... No, in fact, 8 is just nonsense. 8 is absolute nonsense, and so is 7 and so is 6. And the reason for these all being nonsense is there aren't enough ways of making them. 8 and 7 have not got 3 different ways of making them. The only way of making 7 is 1, 2 and 4. There are 2 ways of making 8, so in theory, if this was an 8, I could make that sum work, and I might be able to make that sum work, but I definitely couldn't make it a 3rd different way. 8 in 3 different digits is, well, if you're using different digits, it's either 1, 2, 5 or 1, 3, 4. So we can get rid of 6 is only 1, 2 and 3, so that's even worse. So this digit... Yes, this is really lovely actually, this is quite interesting. If this is a 5, it also breaks for a different reason. Because now we can't make 3 different digits add to 5, 3 different digits, 1, 2 and 3, add to at least 6. So the 5 would have to be part of the sum. Well, how is that going to work? The answer is, it's not. And what is the way to show that? Well, yeah, the simple way to show it is that we've got to add 2 digits to the number 5 in purple. And let's pick the lowest 2, 1 and 2. So that would get us to 8. Now I've got to pick 2 digits to add up with the 5 in yellow. Let's pick the next 2 digits I could go, 1 and 3. Well, they add up to 9. Now the next digit, the next sum, even if I could reuse the numbers, the lowest possible total we could take is going to add a 1 and a 4 or a 2 and a 3 to the 5 and get to 10. So the 5 doesn't work either. And now we are getting into exciting territory because I'm down to 1, 3 and 4 now. I don't know, by the way, if this is what I'm meant to be doing, but I'm finding it interesting, so I'm just going to carry on. Now, 4. Can I disprove 4 in the middle? That might be more challenging. So, if we have 4 in the middle, we know that 4 is part of the sum. It can't be the total. So, where am I going to put 6 in the box? That's an interesting question. 6 cannot be added to 4 to get to another number because we can't put 10 in any cell or 11 or anything higher than that. And we can't make 6 from 3 different numbers, including a 4. So the 6 must go there. Right. Now it's getting even more interesting because we know in this box the totals, i.e. the numbers we're aiming for, must be 7, 8 and 9. So 7 is going to be 1, 2 and 4. 8 is going to be 1, 3 and 4. And 9 is going to be 2, 3 and 4. But we've only got 2 shared cells. We've only got 2 shared cells. So that can't work, can it? No, because no, it doesn't work. It doesn't work. And it doesn't work because in the 7 clue, let's just decide. I don't think it's going to matter which one we decide is the 7. In fact, probably the best one to choose is this one, because that's going to allow me to lend a 1 and a 2 to 2 different other numbers. Oh no, maybe this can work. Wow, wow. No, that's not, actually it doesn't work. It only just doesn't work though. That's really close to working. Let me just think about this for a second. Again, I'm not certain there's a more elegant way of demonstrating this. So 7 will have to use the 1 and the 2, and I can only share one of those digits with another number. Okay, that's very clear, because if this was the 7, you've only got the opportunity to lend a digit to yellow. You haven't got an opportunity to lend anything in purple to blue. So each time you're doing a sum, you can lend exactly one part of that sum to one other digit in these 2 cells. So the 7 is going to be able to lend a 1 or a 2, but it can't lend both. And that's really it, isn't it? Well, the only other way it could work, actually... Yes, I now have understood it. Right, okay, gosh, that's really quite difficult. So if we put the 7 here or here, it's definitely broken, because we can only lend the 1 or the 2 to one other number, but we need to lend both the 1 and the 2. We need to lend the 1 to the 8 to make that work, and we need to lend the 2 to the 9 to make that work. So let's just play that out. So we'd have to lend 1 and 2, you can see. So for the 8, we could make this a 1, and this would be 3, 3, 8. This would be 8, and this would be 3, but now we can't use the 2 to make the 9 work, because the 2 is hypothecated off in the corner. Now, the problem here, the difficulty with this, is what would happen if we put 7 there, which would allow us to lend the 1 and the 2 in 2 directions. And this, I think, only doesn't work because of Sudoku. But I might be wrong about this, so I'm just going to check this. You see the 2 here forces this to be a 2, and that forces this to be a 1, and now Sudoku forces it not to work. That is really difficult. Because now what happens is, where are we going to put the 8? The 8 has to be here, but that's going to mean we need a repeated 2. Wow. Wow, 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 wow. So, I've managed to get rid of 4. That was not easy to do, though. I will accept that. So, now I think 3 is going to be even harder and perhaps impossible to get rid of. Although, hang on, can we just get rid of it instantly? Because what do I do with 7 now? That's a good question. If the repeated digit in all 3 sums is 3, I can't make any of these sums add up to 7, so I have to put 7 there where it can't go. That was much easier than I thought. Right, okay, so this is a 1 we've learned, which gives us a 1 and a 9 over here. Now do we... Yes, we do. We know there's a 1 on any 6 circles, so that's a 1. Now we know there's a 2 up here. That might be very interesting for the middle box. We know there's a 1 over here now by Sudoku. I've got a 1 here and a 6 here. So we know there's a 1 over here by Sudoku and a 6 over here. And a 1 over here. 6 is in one of those cells. Okay, now the thing I've just noticed here is about 2. Where are we going to put 2 in this box? Because 2, look, cannot actually be a shared digit now. It's got to be in one of those positions. And that feels to me like it's going to put an awful constraint on the possibilities for this box. 2 cannot be a shared digit. And we know that 7 and 8, look, can't go in this square. So 7 and 8 are definitely totals to which we are aspiring to get to. Right, so the 7 is 1, 2, 4 for certain. And then the 8 can't use the 2 because the 2 can't be a shared digit. So the 8 is 1, 3, 4. So the 7 is yeah, so the 7 is 1, 2, 4. The 8 can't use the 2 then, so it's 1, 3, 4, which implies the 7 and the 8 are sharing the 2. The 4, sorry, what am I talking about? The 4. So that means that the 4 is not available for anything else. And the 2 is not available for anything else, which means 6 is not a possible sum. So 6 is going here in the corner. And just to re-explain why that's the case, it's because we know that we can't put 7 in the corner here. So we know that one of these is adding to 7, and therefore it needs a 2, and therefore the 2 is in one of those 3 cells, where it's just used by the 7 sum. It's not used by anything else. So it's not allowed to be used for a 6 sum. If we put the 2 there and then decide, okay, we want to try and put a 6 here, for example, we can't, because I can't reuse the 2. So we know one of these 2 squares is a 4, but I don't know which one. And now we know also, so now presumably I can get a handle on the 9, because I now know 9 is not here, so I know 9 is one of the digits I'm summing to. I'm using 1, so it's either 1, 2, 6, which it's not because I can't reuse the 2. So it's 1, 3, 5 in one of these triples. 1, 3, 5. 1, 2, 4. I see, so this is a 3, 4 pair. That's the point, isn't it? Because the 3 is getting shared by the 8 and the 9, and the 4 is getting shared by the 7 and the 8. Wow. Okay. Right. Okay. So hang on. Let me just think. So now that's an 8. That's what we've learned. 8 has to go there. One of these squares is now a 2. One of these squares is an 8. This can't be 7 because of this 7. So the 7 is in one of these squares. But we know that 7 needs a 2. So this is not the 7 because we can't put a 2 here. So this is the 7, this is the 2, this is the 4, this is the 3, and this is a 5 and a 9. I hope that logic was all clear. It wasn't easy actually, but it was very beautiful. Now I've got to put a 2 in one of those cells. Now that's triple there is a 1, 2, 3 triple. Now 6 is restricted. Look, 6 can't go there. So 6 is in this domino. Okay, now I can see 7 has to be in that domino, which means 7 is in one of those 3 squares. And what else have we got here then? Have we got any other magic going on? The answer is I don't know. I now know there's a 1 in one of those 3 positions. So if the 7, the problem is I don't know which way round these go. Except now, that's interesting. Whichever one of these is 9 couldn't go with the 1, because it would have to also have a 6 in it. It would have to be 9, 1, 2, 6, because the 2's in both sums. So whichever one of these is 9 doesn't go with a 1. That means 1 is not in the middle, because 1 is a shared digit for both sums. So the 1 is moved into one of 2 places now, and it forms an X-wing with the 9, wherever that goes. Which means the 7 does go with the 1, and therefore there is definitely a 4. So we know that one of these is 7, 1, 4. But we know the 9 isn't allowed to use the 1. So doesn't that mean that this square here is a 4 always? I think it does. And that's beautiful, because that means that the 4 down here has to be horizontal, where it goes with its friend the 7. So that means this is a 4 and this is a 9. Which means 4 has moved over into one of these squares. I was about to say they're known, but they're not known at all, are they? But maybe I can get now the 9. Yeah, now I can get these 2 squares. This is a 1, 3 pair, because now we know the 9, wherever it lives, is adding 2 plus 4 plus another digit to get to 9. So this has become a 1, 3 pair. That gives us a 1, 3 pair in row 1. 3 is now forced, 3 is now forced into this domino, where it meets its friend the 2. So this is a 2, 3 pair. There's now a 2, 3 pair in that row. These squares are exactly 5, 8, and 9. That means this is a 9 by Sudoku. Okay. And now what do we do? Now we have to think again. I don't think that can be a 7. How could that be a 7 and join up with this? If it's a 7 and this was a 5, that would have to be double 1. That doesn't work. If it's a 7 and this is a 9, this has to be still double 1, just because we're adding. Yeah, so this is not 7. That's 4. 4 and 5 won't work. There's just no way. That's a 7 now. 4 and 5 can't be part of the sum, because 4 plus 5 is already 9, and we're still going to have to add another digit. And if one of them is the sum to which we're aspiring to get to, you'll have to put a 0 in one of those digits. So this is 9. This is 5. Which means the 9 is what we're heading towards. These 2 squares add up to 5. Which means that can't be a 1, because then this would be a 4. So this is now a 2, 3 pair, which means this is not a 6. Now I've got a 2, 3 pair here, which means these squares are 5, 6, and 8. I mean, you can sense the deviousness that must inhabit Udokos's life. I mean, coming up with stuff like this is just... it's Moriarty-esque is what it is. Okay. So now we know there's a 1 on this dot over here. Look, I've got a 3, 5 pair. I can do that. Sorry, I should have done that ages ago. So these squares are 5, 7, and 9. And these squares are going to be the even numbers then, 4, 6s, and 8s. Let's get rid of 8s from these. So does that mean we can... yeah, we can rule 6 out from these 2 squares. Because we know that 6 is either... we know that the digits that accompany 6 on a white dot are 1s, 2s, 3s, and 9s. and whichever one of these we made 6, the other digit would not be a 1, 2, 3 or a 9. So you can't have a 6 in those. So that means this is 6. Now we can maybe do more with this. Well, yeah, okay, now we know we're summing to 8 and we're using 4, so this must be 1, 3, 4. Whoops. Which means we can get rid of the 2. We can place the 2 here. That's going to be helpful because that's going to give me this stuff and this stuff. Now this triple at the bottom must be 1, 2 and 4. That's not a 2, look. 6. Double 1. Oh, it is. No, it's not. That wouldn't work. I was about to say this is. Oh, I've made a mistake, I think. This square here, what am I going to put in it? 6. If I go double 1, 4, that doesn't work. It can't be 6, 1, 2, 3. It can't be 9 here because I can't put 2 there. Oh, good. Oh, it's 8. Ah! I didn't even think of it. I didn't even think of it. This is an 8. And that does work. Good grief. If this is 8, you can double 1, 6 it. Oh my goodness. This puzzle is... Honestly, how has this not been a variant before? It's absolutely beautiful. And it's really intricate. There's some very interesting stuff here. Now I must be probably going to use this dot now, I think. Let me just stare at this for a second in case I'm missing some simple Sudoku, which is almost certainly the case. Don't know. 5, 6. Can't see how to resolve that. Right, let's have a look up here then. So these squares are 4s, 5s, 7s and 9s, which might matter for this one. 4, 5 come out. So what does this mean for this? So if we're heading towards... If we're going to 7, which is possible, yeah, okay, one way to think about this is because these are all in the same box of a Sudoku, we must be heading towards a total of either 7 or 9, because we can't put 7 and 9 in this shape together because the maths won't work. So if we're heading towards a 7, this would have to be 7, 4, and this would be a 1, 2 pair, which would give us a quadruple in column 2. If we're heading towards 9, it gets more complicated because 9 and 4 could work with 2 and 3 here. Bother. 9 and 5 could work with... okay. 9 and 5 doesn't work because this would have to be a 1, 3 pair and this cell would have no value. So actually, can we get a handle? Is there a digit that's well, actually, let's stop there. We know that these squares are selected from 1, 2 and 3. That gives us a 1, 2, 3 triple in the column. So this square's a 4, that square's a 2, that square's a 4, that square's an 8. 4 is now definitely in one of those cells. And let's just come back. I want to check whether there's a digit. Well, we can see actually from the column there's definitely a 2 in this domino. Yeah, okay. 1, 2, 3 triple. The 2's definitely in this domino. There's a 2 there, so that's a 2. So that's a 2. These two squares now look like they're going to have to be 5 and 7, which we can fill in actually. 5 and 7, that's not 5. That's not 7. So that means we get the 7 and the 9, which gives us a 4 here, which means this... Oh, I was about to say that can't be a 9, but that's not true. This still has 2 options. It could be 7 and 1 or 9 and 3. That's a bit surprising. Okay, this 4 is giving me a 4 and an 8 over here. That's not a 4 anymore, which we already knew if I'd thought about it. The thing I'm slightly perplexed about here is I feel like I've used all the clues. So it must just be Sudoku I'm missing, I think. What about those cells then? 6, 8s and 9. So that's an 8. This is a 6, 9 pair. And this square, that square's a 1 or a 3. So I can see I've got pairs here, I've got pairs here, pairs here. 8 I can place in that box. It's got there's actually 4 8s looking at box 1, so that must be an 8. So there's definitely a 6 in one of those cells. 5, 7, 9. Okay, now I'm confused. I don't actually see how to solve this. Oh, I see. No, I've just spotted what I've missed. Okay, once I got that this was a 9, look, this is now resolved. 2 plus 4 plus 1 does not equal 9. So that's a 3, that's a 1, that's a 1, that's a 3. That's hopefully going to do some damage over here as well. It gets me a few more digits at least. Now, I see. Now this is a 3, 2, 4, which means it's adding up to 9. That resolves that and that and that. That's become a 7 out of nowhere. That's a 7 by Sudoku, which means that's a 6 by Sudoku. This 7 is giving us a 7 and a 9 and a 5 and a 6. And that is how to solve a very, very, very good puzzle indeed. Wow. I loved that. That is so interesting. I'm not sure. This central box, it sort of felt like a bit of a sort of magic square exploration, but I think that there is going to be a more elegant way of proving that this central square has to be a 1. The way I did it was a bit exhaustive, and I think the logic was, it felt like it was clean, but it didn't feel like it was necessarily efficient. And I suspect that there is a more beautiful way of figuring that out. So do let me know in the comments if you found a clever way. I do enjoy reading them, especially when they're kind. And Udakos needs to take a bow for this one. And I think this will be a variant we see more of on the channel because it's really, really cool. Thanks so much for watching. And we'll be back later with another edition of Cracking the Cryptic.